You've probably seen a ball fall, I don't know, 1,000 times, but have you ever stopped to think about what's really going on from a physics perspective? Today, we're going to go way beyond the simple answers. We're breaking down the complete physics of a falling object, from the very instant it's released to the moment it hits its final speed. Think of it as the story of a falling ball, told through the lens of AP Physics.
So, let's kick things off with a question that seems super simple on the surface. If you just drop a ball, does it fall at a constant acceleration? Now, if you've been in any physics class, your brain is probably screaming, yes, of course, it's 9.8 meters per second squared. But the real world has a little twist, and that's where things start to get really interesting.
All right, let's start our story at the very beginning, the absolute first instant, the moment the ball is let go. We'll call this time 0, or t equals 0. At this precise moment, what's happening? What forces are at play?
Okay, so at this one tiny, precise instant, the ball is, for all practical purposes, motionless. Its velocity is 0. And because it's not actually moving through the air yet, there's only one force that truly matters here, that relentless, downward pull of gravity.
So this force of gravity, Fg, you probably know it as the ball's weight. We calculate it by multiplying the ball's mass by the gravitational field strength, which we call g. And for this entire fall, for our purposes, we can think of this force as being totally constant, an unchanging force pulling straight down. It's really the main character in this story.
But you know, the very second that ball starts to move, our simple picture gets a whole lot more complex. A new force jumps into the scene, and it's ready to challenge gravity's total dominance.
And this new force is, of course, air resistance, or what physicists often call drag. Now, here's the absolutely crucial difference. Unlike gravity, air resistance is not constant, not at all. It's a dynamic force. It actually gets stronger as the ball moves faster, and it always acts in the direction opposite to the ball's motion.
So what we've got here is a classic showdown, right? It's a tug of war. We have gravity pulling down, and now we have air resistance pushing up. And this creates this dynamic battle where the balance of power is constantly shifting as the ball falls.
In the very first moments of the fall, the ball is still moving pretty slowly, and that means the upward push from air resistance is, well, it's pretty weak. Gravity is the undisputed champion at this point, easily overpowering that tiny little bit of drag.
But as the ball picks up speed, that force of air resistance starts to fight back harder. That upward force gets bigger and bigger. Now, gravity still has the advantage, for sure, but its lead is definitely shrinking. The two forces are getting closer and closer to being evenly matched.
And this whole situation brings us to the key concept for understanding how things move, net force. You got to remember Newton's second law, F net equals mass times acceleration. It's not just one force we care about, it's the combination, the vector sum, of all the forces that actually determines how an object accelerates.
So here is the crucial takeaway. Because gravity is still winning that tug of war, the net force is still pointing down. And what does that mean? It means the ball is still accelerating, it's still speeding up. But, and this is the big but, because that net force is getting weaker and weaker, the rate of acceleration is actually decreasing. And that, right there, is the answer to our first question. The acceleration is not constant.
So where does this all lead? The ball gets faster, air resistance gets stronger. What's the end game here? Well, eventually, we reach a point of perfect equilibrium, a stalemate.
Eventually, and this is bound to happen, the ball is moving so fast that the upward force of air resistance grows to become exactly equal in strength to the downward force of gravity. The tug-of-war ends in a perfect draw.
And with these two forces perfectly balanced, their vector sum, which is the net force, is now 0. A big, fat 0.
Now, this is such a critical concept in physics, so let's be really clear. According to Newton's second law, if the net force is 0, the acceleration must also be 0. This doesn't mean the ball suddenly stops in midair. No, it just means it stops speeding up. It continues to fall, but now it's at a constant maximum speed that we call terminal velocity.
Okay, so I think we've got the falling ball down pretty well. But to really test our understanding, let's flip the script. What happens if, instead of dropping the ball, we throw it up into the air first?
So I want you to really think about this for a second. The ball has left your hand. It's moving upward. Which way is the net force pointing? Is it up? Is it down? Does it maybe change? What do you think?
All right, let's break this down. The velocity is obviously pointing up. That's the direction it's moving. Gravity, as always, pulls straight down. No surprises there. But what about air resistance? Remember the rule?
It always opposes motion. So if the motion is up, that means air resistance has to be down. So in this case, both forces are actually gagging up on the ball, pointing downwards together.
This just hammers home one of the most fundamental rules in all of physics. You can never, ever assume that the direction of an object's motion is the same as the direction of its net force. An object can be moving up while it's accelerating down. It's the acceleration, the change in velocity, that tells you the true direction of the net force. And with that, we'll end with a classic thought experiment to really test your new expertise. So, imagine you're in a vacuum. No air resistance. A feather and a bowling ball are dropped from the same height. They hit the ground at the exact same time. Your challenge is to use everything we've just talked about, net force and gravity, to explain exactly why that happens. Give that some thought, and thanks for joining this explainer.